Notes for, this is actually for square roots, okay? But I'm going to look at our last rule of rules of exponents first. All right, now before I do this, you guys all know the square root of 4, right? What is the square root of 4? Why is it that? Because 2 squared is 4. What does this mean? How many factors of 2 did I need to get 4? I needed 2 factors of 2 to get 4. And so, and we'll talk about how to do this in a second. Square root of 4 is 2. Square root of 9 is 3. Does anybody know what the cubed root of 8 is? Sorry. It's 2, because 2 cubed is 8, right? All right, now that you know that, that's going to help as we talk about rational exponents. X to the a over b is equivalent to, well, first off, it was just x to the a, I would say I had a factors of x, right? I still have a factors of x, but the b indicates how many roots I'm taking. B is the number of roots. Fractional exponents, the way that they're set up for our notation to understand them, fractional exponents, if you have a denominator, the denominator in your exponent equals the number of roots. So let me give you an example. I have 9 to the 1/2. Okay, I'm going to put that in my calculator. 9 caret 1/2. If your calculator doesn't automatically put it in the exponent, then you're going to have to put that in parentheses. The 1/2 will have to be in parentheses. You're going to get 3. Okay, let's look at y. You're going to get 3. Well, wait a second. What is 9? Really, it's 3 what? 3 squared to the 1/2 power. What do I do when I have an exponent on top of an exponent? What do I do with them? Multiply them. What's 2 times 1/2? 1. 3 to the first. That's why this is working, okay? What's the cubed root, or 27 to the 1/3, which is actually the cubed root of 27? The reason being, this 27 is really 3 cubed, right? Well, what's 1/3 times 3? What's 1, right? It would be 3 to the first, which in this case, the cubed root of 27 is 3. 27 to the 1/3 is also 3. Nope, I did that wrong. I did 28. There you go, is also 3. Let me pick a different number. What about the third root of 64? What's 4 times 4? 16. What's 16 times 4? 64. So really, that is the cubed root of 4 cubed, which is 4 cubed to the 1/3 power, which is 4. So I do this because I have people all the time who are like, Mr. Ritter, I can't find the cubed root key. We're like trying to take the cubed root of a number like 125. I'm like, oh, do the cubed root of 125. I'm like, well, we could do this with prime factorization, which is a skill we're going to work with in a second. But they're like, as they're solving a problem, they're like, I don't have a cubed root key on the calculator. I can't find it. Well, you can rewrite this as 125 to the 1/3 power, which I already know happens to be. Does anybody else know what it is? What? 5, because 5 times 5 times 5 is 125. So, but that's how rational exponents work. So if you have a rational exponent, the denominator of your exponent is actually telling that you're taking that many roots of x to the a. All right, now we move on to the actual notes, if I can find them. here they are. Radicals, Radicand. The learning targets that we're looking at specifically today are to be able to write radical expressions in simplest form using perfect squares or prime factorization, using product property and quotient property. Tomorrow we're going to look at the other three. If we can get to addition and subtraction today, we will, but, oh, I have it right here. So you should have picked a copy up when you came in. That was pre-calc. It had gotten switched. They're over on the desk over there. So a couple things to note is that the number underneath is called the radicand. Okay? This is the, this right here is called the radical. That right there is called the radical. In this case, which one of these is the radicand? The radicand is 4. And what's the root? 3. So we know the terminology. When you hear the word radicand, you know what we're referring to. The root, you know what we're talking about. The radical, you know what we're talking about. When we go to simplify radical expressions, what does it mean for it to be simplified? It means a couple things. These other two are going to be more relevant tomorrow. The radicand has no perfect square factors other than 1. There is no decimal value under the radical. The radicand has no fractions within it, so the radicand can't be a fraction. And there can be no radicals that have square roots in the denominator. Okay, so I can't have any radicals in the denominator. We're going to talk about that part tomorrow on how to rationalize the denominator. Before we get to the U-try problems, and I think these are all perfect or they're going to work out, they are. We need to talk about simplifying by factors. Now, a lot of you already know your perfect squares and perfect cubes, apparently, so that's great. So that might help you out for some of it, but there's two ways to do this. We can simplify by prime factorization, or we can simplify using perfect squares. Here's how prime factorization works. I'm going to write prime factorization of the number, and then use rational exponents, fractional exponents, to reduce. All right, so we have, so here's an example. I'm going to have the square root of 400. I picked this number on purpose. Some of you already know how to break it down, but we're going to do it this way. So I got the square root of 400. We're going to do the prime factorization of 400. So I just start by pulling anything out I can. I know that it's 4 times 100. I know that 4 is really 2 times 2. I'm going to circle all my prime numbers as I break it down and stop once I get to all primes. My 100 is really 2 times 50. My 50 is really 2 times 25. And my 25 is really 5 times 5. Any questions on that? Oh, 25 wasn't prime. I should not have circled 25, sorry. 25, pretend that that's not circled. We only want to circle our primes. So in this case, how many factors of 2 do I have? 4. So since I have 4 factors, that's really 2 to the 4th. And how many factors of 5? 5 squared. Well, I'm going to use a trick that I really haven't taught you yet, but that's okay. We're supposed to be able to separate these. This is multiplied. And really, what is this radical right here? Actually, I'm not going to use it. I'll use the rules we've learned so far. What can I rewrite this as? 2 to the 4th times 5 squared raised to what power? Nope. What's the root here? We didn't talk about it. Sorry, I totally skipped this. You know how the 1 is hidden in multiplication and the 0 is hidden in addition? Well, When it's cubed root, we write cubed root. When it's fourth root, fifth root, we put the root in there. When it's square root, we don't put the 2 there because it's like, why? What else would the square root mean? You're not going to do the first root. So if it doesn't have, is the square root. So what would this really be? To what power? Not to the second, but to the 1/2 power. The number there would be 2. So this is really an exponent of 1/2. Remember, we just talked about this. The square root, taking the square root is the same as raising the number to the 1/2 power. It's fractional exponents. That's what that means. What do I do when I have exponents on top of exponents? Multiply them. What's 1/2 times 4? 2, so that's 2 squared. What's 1/2 times 2? 1, so that's 5 to the first. So this gives me 4 times 5, which is 20. Now there's another way, a more efficient way to do this, but this technique right here works really, really well when we have variables. And it works really, really well when we have cubed roots and fifth roots. So I'm going to do one that's a cubed root in just a second. I don't want to do the number that big, yikes. We'll do 216. And then I'll do one more that has some variables. We'll do actually 216 y to the 6th. And I'm going to do the cubed root of this. Well, I actually would split this up. I'd look at this as, I'm not going to split it up. I will split it up later, but right now we're going to do this. 216 breaks down. Does anybody know a number that goes into 216 other than 2?
1.
Well, 1 does. That doesn't help me break it down. Yes. 108? Okay, well that's 2, but that's okay. 4. 216 divided by 4. That's helpful. So we'll do 4 and 54, because the 4 then breaks down to 2 by 2. The 54, anybody know a number that goes into 54 other than 2?
1.
Well, that's 2. No, it's not 6. 9 and 6. There we go. 9 and 6. 9 times 6 is 54. Thank you. It just saves me from making my factor tree longer. But it doesn't matter. You'd still get the same prime factors. And this is 2 by 3. Any questions on how I did my factor tree? So 216 is really 2 to what power? 2 to the 3rd times 3 to the 3rd. And then I still have that y to the 6th. So that's times y to the 6th. And we're taking the cubed root, right? So that's really raising all of that to the 1/3 power. 2 cubed, 3 cubed, y to the 6th to the 1/3 power. And you already know your rules of exponents. So when I distribute that in, I just get 2 times 3 times y squared. And 2 times 3 is 6. So I can get my answer this way. Yes? Which 3? This one? This one? This. See, it's the cubed root that we were taking. So the rule is that the denominator of our fractional exponent will be whatever the root was. Up here? I put it there. I made that problem up. I made it a cubed root. I started as square root, but I wanted it to be a cubed root. All right. Let me give you one other one that doesn't work out as nicely. We're going to use 24x to the 7th. What goes into 24 that's not 2? 6 and 4. 6 is 2 times 3, and 4 is 2 times 2. Oh, and I wanted to do this as a, we'll just leave it like that. I'm good with square root. We'll leave it as a square root. I don't care. All right, x to the 7th. So 24 is really 2 cubed times 3. I don't want to, let's do this as a cubed root. Please change it to a cubed root problem, because I don't want to get into all that right now. Times x to the 7th. Any questions on how we went from here to here? So I just did prime factorization of the 24, that's it. So if I'm doing the cubed root, it's really saying that this is 2 cubed times 3 times x to the 7th raised to the 1/3 power. Yes?
So if it's like, so depending on what the root is, then it's going to be 1 over what the root is.
Yes, so if it was square root, then it would be 1/2 power. If it was 4th root, it would be 1/4. We're only going to be doing square roots, but I want to show you because this is going to lead to what we do later in the year in an Algebra 2. Okay. So if I distribute this, that's just a 2. This is 3 to the 1/3 power because I'm just distributing that, right? What about this one? That would be x to the 7/3, right? You guys see that? X to the 7/3. Now I'm going to probably have to write it up here because I'm going to run out of room on my paper. I'll write it underneath and then above. That's 3 to the 1/3. There's one factor of 3, right? See the 3 to the 1st? What is 3 to the 1/3 really? No. That would be 3 times 1/3. What does the 1/3 really mean? It means I'm taking what? The cubed root. And since I couldn't, since nothing went away, I have to leave the cubed root of 3 there. The 2 doesn't have a cubed root. This is 2 to the 1st. This is the part that's tricky, the x to the 7/3. How many times will 3 go into 7? 2 with a remainder of 1, right? So what that means is I actually have x times x times x, because there's 7 of them, x times x times x, and x. Do you guys see that? And since I was doing 1/3, it says I have 2 groups of 3 and then 1 remaining. That's x to the 7th, right? Well, wait, those groups of 3, if I raise those to the 1/3, they would each be 1, right? I'd have 1 factor. If I look at this as x cubed to the 1/3, and this one as x cubed to the 1/3, and this as x to the 1/3, I'm just regrouping it. What's 3 times 1/3? 1. So this would come out, this would just be x to the 1st. This one would just be x to the 1st. And what's x to the 1st times x to the 1st? X squared. So I actually need to work that in front of my 2 here on the outside. I ran out of room. I'm going to have to write it above. I'd actually have 2x squared. Under my cubed root, I still have that 3 that didn't come out. And see how I still have this x to the 1/3? That can't come out either, so that x stays under also. I'm going to show you on a different piece of paper because it's getting too jumbled on here. Shh. We're just going to do the square root of x to the 9th. What is that really? That's x to the 9 halves. Does that part make sense? You guys don't have to write this down. I just want you to follow along. Does that part make sense? All right, I'm going to regroup this. Now, that's really, how many times does 2 go into 9? 4 remainder 1. Well, watch this. That's 4 groups of x, because there's x times x, x times x, x times x. That's 6. There's 8. There's 9. Notice that that's 1 group of 2, 1 group of 2, 1 group of 2, 1 group of 2. So I have 4 groups of 2 and a remainder of 1. Yes? Because that was x to the 9th, the square root, and the square root is 1/2, right? So now, what's x times x? That's x squared, right? I'm just regrouping this. I'm showing you exactly every step, but I'm going to show you a shortcut to this in a second. That might make more sense. These were all raised to the 1/2 power, right? So that's 2 over 2, that's 2 over 2, that's 2 over 2, that's 2 over 2. This is 1 over 2. X to the 9 halves, there's my x's multiplied out, right? X squared times x squared times x squared times x squared times x to the 1st. but they all have the denominator of 1/2. What's 2 over 2? 1. So this is really x times x times x times x times x to the 1/2. There are 4 of these, so that becomes x to the 4th. The x to the 1/2 is the square root of x to the 1st. Did the grouping part make sense? I have 9 x's, right? See how I have 9 x's there? And I have 4 groups of 2. And when I divide that exponent by 2, because that's what this part says right here, that's why I have the over 2, these become x's, and they become x to the 4th. Look at that number, 4, x to the 4th. There's a singleton remainder that I can't divide because 1 is not divisible by 2. It remains as x to the 1/2, which is the same as the square root of x. So if you look at this, when I do this, I have x to the 4th, and I have a 1x remaining under the radical. So the idea behind this is if I told you to do the square root of x to the 5th, well, that's x to the 5/2, right? How many times does 2 go into 5? 2 with a remainder of 1. So guess what I'm going to have outside my radical? X squared. I'm going to have 2 factors of x escape and 1 remain under the radical. And the whole reasoning behind this, though, there were 5 of these, right? Just look at x to the 5th. X times x times x times x times x. I'm taking the square root, so 2 of them, right? That's x squared to the 1/2. That's x squared to the 1/2. That's x to the 1/2. This is x times square root of x, which is x squared to the 1/2. This is why it works, but the simple rule is if you do that fractional exponent, 2 x's escape, x squared, 2 factors of x escape, 1 factor remains under the radical. So I'm going to put that at the bottom of this sheet because I didn't really show that. For things like this, if I have if I have the square root of x to the 11th, that's really x to the 11/2. And how many times does 2 go into 11? 5, with a remainder of 1. What this means is 5 factors of x will escape. 1 factor of x will remain under the radical. There's a different way to look at this. You know how we did this as prime factorization? There's a quicker way. How many of you know your perfect squares? Okay, if you don't, you're going to want to, because in geometry we mostly use square roots. And here's why. If you know your perfect squares, all you have to do is divide out the highest perfect square and break it down. Divide out the highest perfect square and break it down. So let me show you an example of what I'm talking about. But first, let's talk about our perfect squares. 1, 4, 9, 16, 25. How did I get those numbers? How could I generate this list? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, 13 squared, 14 squared, 15 squared. In pre-algebra, which should have been included in your 8th grade math, you were supposed to memorize the first 15 perfect squares. Okay? Right? By the way, most of them, you know your multiplication tables, so you could get. Shh. The 13th is 169. The 14th squared, you just switch the last 2 numbers from the 13th squared, and then 15 squared is 225. So here's the thing. I'm going to give you a number like, well, if I ask you for the square root of 16, that's pretty obvious. What's that? 4, because 4 squared is 16. But if I ask you for the square root of 32, Well, a lot of you are like, well, that's not a perfect square. I'll do prime factorization. I'm not doing prime factorization. Here's what I'm doing. Shh. What perfect square goes into it? What's the 5 is not a perfect square. 25 doesn't go into 32. 16. 16 is the largest perfect square that goes into 32. 16 times what? Times 2. I need to put them both under a radical. And we'll talk about this product rule in a second. I should have probably covered it first. Square root of 16 is what? 4. So did I have to do prime factorization to figure that one out? Not if I know the perfect square that goes into it. Just like the square root of 400. What perfect square goes into 400? 100 times 4. Well, wait a minute. Those are both perfect squares. So that one's 10, and this one's 2. 10 times 2 is 20. Is this more work or less work than what we did up here? A lot less. Now, I still have people who like this method. Shh. And when you get to cubed roots, this is probably a better method. But if you can do square roots and you know your perfect squares, then you're good to do these problems.
Wait, how did you get 10 times 2?
10 times 2? Well, the square root of 100 is 10. The square root of 4 is 2. So now that they've escaped the square root because I had an answer to them, I can multiply them together. So go ahead. Let's take a look at these problems. Go ahead and give letters A, B, and D a try. A, B, and D. We'll talk about C in a second. The answer for A. Yes, sir. 9 is correct. It's on our perfect squares list. What could I do for letter B first? Yes. Divide 27 by 3. I get the square root of 9, which is 3. That's easy enough. Y to the 4th. This one I like to think of as a fractional exponent. It's y to the 4 over what?
1.
Nope. 4 over 2, because the square root, that root becomes the denominator of our x in exponential form. And what is 4 over 2? So that's really y squared. Now I do have some people who say, I don't like doing it that way. Can I do it this way? And I say, sure. Can I say, hey, wait a second, that's really y squared times y squared. And the square root of y squared is? What's the square root of y squared? Y. So then they still end up with the right answer, but it's a different way to think about it. It takes a little longer, though. Yes?
Could you also write it as y to the 4 times 1/2?
Y to the 4th raised to the 1/2 power is the same thing, yes. And that's y squared, yes. See the negative 144? Square root of 9 is 3 because 3 times 3 is 9. 12 times 12 is 144, right? So that's 12. But if I made it negative 12 times negative 12 is positive 144. There is an answer to this, but we need to talk about that later. We're going to table that for now. This one for now is not real. I don't want you to say no solution. There is a solution, but it's not a real solution. So no, it's actually imaginary, and there are imaginary numbers. Shh. All right, we're talking about, no, it's different. It's completely different. We'll get there later. Product property. Shh. Guys, we're already pushing it with this lesson. It's a packed lesson. You're talking on the side doesn't help. If you have a question, raise your hand. Product of roots. We've already done this, except we did it in reverse. The square root of A times the square root of B equals the square root of A times B. We did this in reverse, right? We said the square root of 400 was the square root of 4 times the square root of 100, right? Well, I can also, that's what we had done when we simplified that one problem. So we did this. We started with a number and we split it into two. This rule works two ways. You can start with one radical and split it into two by multiplication, or you could start with two radicals, like the square root of 3 times the square root of 6. And I could put that together. That's really the square root of what? 18. So right now I use the product rule to put them together. Now I'm going to simplify it by splitting it apart. What goes into 18? That's a perfect square. 9 is the perfect square, and then 2. No perfect square goes into 2, so I know I picked the highest perfect square. The square root of 9 is 3, so 3 square roots of 2 is my answer. The product rule works two ways. You can multiply them together to get something, and then you can use the product rule to break it down. Yes, sir?
Yeah, I got everything. I got 9 and 2. But then how did you get 3 outside?
Well, what is the square root of 9? That's why I'm picking a perfect square to divide out of it, because if I know the square root of 9, I can say what it is. That's how I got the 3. Same thing on this. I wouldn't leave it like this because the square root of 4 is 2. The square root of 100 is 10. 2 times 10 is 20. You have to simplify all the way. Here I can't go any further because the 2, nothing else will go into the 2. That's a perfect square.
So the perfect square you put outside?
The perfect square, you actually take the square root of it to get it out of the radical. The other one stays under the radical. And then I just need to double check to make sure that nothing else goes into it, and then I can leave it like that. Yes?
What if it was like the square root of 10 times the square root of 2?
Okay, square root of 10 times square root of 2. Let's take a look at that. Square root of 10 times square root of 2 becomes the square root of what? 10 times 2, which is 20. Right? I've just put those together using the product rule of roots. And now I'm going to try to break that down. I know a perfect square that goes into 20. The largest one is 4. The square root of 4 is 5, or not 5, is 2, sorry. And I can't break down the square root of 5. No perfect square goes into it, so I leave it as the square root of 5.
Isn't 5 a perfect square?
5 is not a perfect square. Look at your list of perfect squares. 1, 4, 9, 16.
Like 5 times 5.
Nope. That would be 25. All right, so here we go. Here's 27. We're going to use the product to break these down. Well, what perfect square goes into 27? 9. Square root of 9 times square root of 3. What is the square root of 9? So 3 square roots of 3 is my answer. Now I have this 4. I have to leave it out there. It's not under a radical, but it is being multiplied. I have to break down 98. Does anyone know a perfect square that goes into 98? 2 is not a perfect square, but good news. What would I multiply with it? 49, right? Is that a perfect square? Yep, so it works. If it wasn't, I wouldn't want to use the 2 just to use a 2. Square root of 49 is 7. So this is 7 square roots of 2. But I bring down the 4 also. 4 times 7 is 28. So my answer is 28 square roots of 2. What's up? You can't. It's a decimal. It's a decimal. It's like, no, not even. All right, square root of 960. Well, you might see if there's something on your list. You want the largest perfect square that goes into it, preferably. Preferably the largest perfect square that goes into it. Yes? Yeah. Oh, that's not it. I think I found it. Nope. (16 times 4) 64. I think it's 64. Did anybody else get that? No? What did you get to divide into it? Anybody get a perfect square to go into it? It is, largest one is 64. Yeah, it does. 64 goes into it. But Does anyone have a different perfect square that goes into it? Doesn't have to be the largest one. 2 is not a perfect square, but 4 is. Great, let's do 4. Shh. 960 divided by 4 is 240. What's the square root of 4? 2. Could I break 240 down more? Yeah, what goes into 240? 120. Neither of those is a perfect square, though. 4 will go in again. 4 and 60. 4 and 60, actually. Well, the square root of 4 is 2, right? Could I break down 60? Yeah. What goes into that? 4 again. 2, that's going to be 2. So now I have 3 factors of 2 that I pulled out, and the square root of 15. Nothing will go into square root of 15. That's going to be 8 square roots of 15. Some of you might prefer to do this one by prime factorization because it's so big. But I'm going to tell you, 64 did go in. If you had done 64, which was the largest perfect square, by the way, here's what I would do with that. I would start dividing from the top of my list. Hey, in my calculator, 960 divided by 225 doesn't go in evenly. None of these go in evenly till I get to 64, so that's my largest perfect square that goes in. Shh. What is the square root of 64? 8. I got my answer directly. Much less work if I take out the largest perfect square. If you're not going to do the largest perfect square, you might as well do prime factorization because it's going to take about as much work. 162, does anybody know a watch this, I'm going to split this up. 162 times the square root of y to the 6th. What perfect square goes into 162? 9 goes in, but if 18 goes in, then something bigger than 9 will go in. 81. 81 goes in. Now you could do 8 and 9, or 18 and 9, but then you'd have to break down the 18 further. This is going to be square root of 81 times square root of 2, which is 9 square roots of 2.
So how do you find that biggest?
I divide down my list. I say, hey, 162 is right here on my list. What's half of 162? A lot of you were like, let's divide it by 2. Well, that's, 162 divided by 2 is 81. Well, hey, that's a perfect square. But that'd be a good place to start on my list. Go down the list till I find the largest one. Divide them in until I find one that works. 9 square roots of 2, but this is really y to the 6th raised to what power? To the 1/2. And what's that going to be? Y cubed. So my final answer, 9y cubed, square root of 2. I always put the radical at the end. Always. This is y to the 6th raised to the 1/2 power. The 9 came out of the square root of 81. There's no radical on it anymore. If you did a perfect square, all right, I need to move on, but first I need to know if there are questions, because I hear all these conversations that I asked not to happen, and while I'm glad you guys are talking about math, I need us to be on the same page. So are there any questions about where that came from? Yes?
So for square, when it has the 3 for the root, we're not going to have to do that for this.
For right now, we don't have to do it. We're just doing square roots today and tomorrow. Okay? Yes?
So when you get that exponent on top of y, you have to multiply it by 1/2 because it's like the square root.
Because it's the square root, that 2 became the 1/2 power on that, yes. Does that make sense?
Yeah.
So that's where I got the y cubed. And then I put a number that's outside, and then my variable, and then the radical for my answer. The quotient property is the last property we're looking at, and we've already done a little bit with it for today anyhow. We'll look at other ones. And this is where you have the square root of a number of a fraction, and it can become the square root of the numerator over the square root of the denominator. Or you could start out with this and work the other way if it makes the problem easier. The time that it's nice to separate them is if the denominator is a perfect square. If your denominator is a perfect square, separate them and take the square root of that perfect square. It makes it so much easier to only have to deal with the numerator. The time that it makes sense to combine them is if you have two separate square roots that you're dividing, and this isn't a perfect square, but they have a common factor. Because then I could divide away that common factor before I start breaking them down. So here is an example. I have the square root of 81 over 3. Well, actually no. Sorry, I wanted to change that. We'll just leave it like that for now. We did this type of problem already, right? Is 3 a perfect square?
No.
So would it make sense to separate them? No. Not really. But 3 will go into 81 how many times? Try 27. Could we break down 27? Yes, we've done it a few times today. It's square root of 9 times square root of 3, which is 3 square roots of 3. How did I get the square root of 27? I did 81 divided by 3. Now, I didn't use the rule for this one. What I wanted to show you, I didn't write the right thing down. We have two more that I want to show you. Here's one. I've got the square root of 81 over 4. Is 4 going to go into 81 evenly? No. But even if it did, would I really want to divide those? No, because guess what? If I split it up, the denominator is a perfect square. What is the square root of 4? 2. What is the square root of 81? 9. Even if the numerator weren't a perfect square, I could then work on my numerator, but I always want to try to get my numerator to be a perfect square if possible. So that's 9/2, which can't be reduced anymore. What if I start out with square root of 18 divided by square root of 2? Square root of 18 divided by square root of 2. Are either of those a perfect square? No, but I could divide them, so I'm going to write it together as square root of 18 over 2, which is the square root of 9, which is 3. I just made the problem a little easier. So in our note sheet, that's what we're looking at. I'd like you to try letters A and B, and we'll do D together. But try A and B first. They shouldn't be too difficult. If they're perfect squares, or if the denominator is a perfect square, separate them. You never got what? These are perfect squares, so the denominator is, right? Separate them. Square root of 49 is 7. Square root of 16 is 4. Done. This one's a perfect square, so separate it. 196 square root of is 14. Is there a perfect square that goes into 15? No. So it stays just like that. The last one that I wanted to do is 4/5 times whatever I get from this. Neither of those is a perfect square, but will something go into both of them? 3. Divide them both by 3 to reduce it. I now have the square root of 9 over the square root of 25. So it made sense to keep that one together because they weren't perfect squares. And that becomes 3/5, which is 12/25. On the worksheet that you're going to pick up on your way out, do not do any addition or subtraction problems. There's like 4 on there. We did not get to that skill today. So pick up a worksheet on your way out. Do not do the addition and subtraction problems because I didn't show you how to do those yet. Come see me if you need help.